Welcome to Engineering Innovations, the official podcast of Purdue University's Elmore Family School of Electrical and Computer Engineering. I'm Kristin Malavenda. And today we're featuring one of our PhD students. Paschal Amusuo is a fifth-year PhD candidate in Purdue ECE working on software security. His research uses formal verification and runtime defenses to uncover vulnerabilities before software is deployed. He's discovered 37 vulnerabilities in widely used embedded systems. He's also earned recognition as a Qualcomm Innovation Fellow. So today we'll talk about his journey to Purdue, what it's like being a PhD student, and how his work could reshape how we secure the software that we rely on every day. Paschal, welcome.
Thank you.
So let's start with, where did you grow up, and when did you first realize that maybe engineering is your path?
Okay, where I grew up. So I'm from Nigeria. Nigeria is a country in Africa, on the western part of Africa. And in Nigeria, I grew up in this city called City of Port Harcourt. Port Harcourt is, I think, the second or the third largest city in Nigeria. It's a huge city. It's known for it's where Nigeria is popularly known as an oil producing country, and Port Harcourt is like the base of many of the oil companies. So many persons in Port Harcourt are either fishermen or oil, like they work with oil companies. So yeah, that's the part of Nigeria I grew up in. It was a lovely place. It's called the Garden City because it used to be very green. It's a beautiful place. And when did I first realize I loved engineering? To be fair, I can't really remember the exact moment, because I can remember right from a kid. I used to be the son. Let's say my dad gets a new phone. Mm-hmm. I'm the guy who would take the manual and go read the manual and come and tell him how to use the phone. Right? My uncle got a new car and I go read the manual and I come and tell him, oh yeah, if you want to turn on the music, this is where you press and press.
Right.
So I think right from a kid, I've always been attracted to understanding how things work, how to break things and how to put them together. Yeah. So I think engineering became just like a natural path towards that direction.
What did your parents do? Do you have engineers in your family?
Oh yeah, my dad was an electrical engineer.
Oh, okay. So there you go.
I guess that's
the family business.
Yeah, except my dad is more on the power systems side of things.
Gotcha.
So I guess if I grew up maybe 20, 30 years ago, I would have also been in that line, but I went to the computer line of things because that's
where we are today, right? So what led you to Purdue ECE specifically?
Okay, so after I finished my undergrad, I worked briefly in Nigeria as a software engineer. I think for like 2 to 3 years. And during that period of me working as a software engineer, I started thinking of going to do grad school, precisely a PhD. And one of the first steps is, what kind of school should you want to be in? I think the 2 steps which many persons do, which I did, the first is go look at the rankings and see what are the top 10, top 20 schools in engineering. And amongst those schools, like, you look through each of them. I think the one thing that really attracted me specifically to Purdue was that I saw this very intense focus on engineering, but for practical impact. You know, I came across things like the Discovery Park, the Convergence Center, the schools like centers like Sirius, like the Cybersecurity Center. And there was this huge focus on not just doing research for research purposes, but to solve real-world problems.
Right.
I think that was the first thing that attracted me to Purdue itself, right? Then the second thing that you would also do is to look through the faculty members there. And so when I was looking through the faculty members of different schools, I came across that of my current advisor, Professor Davis. And he does research in software engineering, but more like along the lines of understanding software failures and different ways to prevent software failures. And I already had experience, or I had experience at the time as a software engineer. So it was something I could definitely relate to, something that I saw on his website. And there was this thing about software 2.0. And, you know, how do we ensure that we go into software 2.0, which is software plus AI, where we are now, you know, in a safe, secure way. And I think that really piqued my interest, so I reached out to him. So I think the combination of Purdue having a focus on research for practical impact and Professor Davis doing research at the Center of Software Engineering, AI, and failures and practical, which directly aligned with my background and experience as a software engineer, I think made it the right fit for me.
Great. Yeah. Well, for listeners who aren't software engineers, including myself, what problem are you trying to solve with your research?
Okay, what problem am I trying to solve with my research? I don't know if the listeners or you can remember, sometime in July 2024, there was this CrowdStrike incident. many viewers may not know the root cause of this incident, but I think the manifestation was many of the airlines were down for a day. Many of the banks, financial institutions, it was like the whole internet came to a stop. Now, when you take a step back to ask what caused this, right, it's what we call a memory safety bug. Now, this is very technical, but what this just means is you have your software runs on your computer, it interacts with memory, right? So it stores things in the memory. Now, depending on how the software is written, the computer tells the software, hey, this is just the region of memory you can access, right? So it's more like when you have a student and you give him like, hey, all your notes, write it on just this page. Don't write on other pages. It's someone else's own.
Gotcha.
But sometimes you can have bugs in the software where the software goes on to write on a region of memory that they are not supposed to write on, right? So we call it memory safety bugs, vulnerabilities. And they are very bad because first, the computer is also designed to ensure that if the software tries to write into a region of memory that it's not allowed to write to, the computer just kills the software. It's like, oh, this guy is trying to do something bad. I kill you. Yeah. So that's what happened in the CrowdStrike incident where so the banks, they used a software called CrowdStrike for their cybersecurity protection. And then the software had a bug that allowed, there was some updates, there was a bug that allowed the software to read from an area of memory it was not supposed to read from or write to. And so the computers running this software, which was computers that power most of the world's financial, aviation institutions, they all crashed, right? They killed the software, things were down. So part of my the worst part of this kind of bug is that because the software is interacting with memory directly, if an attacker is able to influence what aspect of region the memory can write to or read from, then an attacker can steal information directly from the memory, or even overwrite sensitive information in the memory, which is also very, very bad.
Yes.
Right. So but this class of memory issues, we call them memory safety bugs, memory safety vulnerabilities, is one problem that my research tries to address. So we try to develop techniques, right, tools, systems, processes, procedures. How do we ensure that this never happens again?
Gotcha.
Right. Yeah.
So your work focuses on things called like formal verification and what you call unit proofing. Explain what those mean and why they matter for making software secure.
Okay. Yeah, thank you. I think that's also a natural progression from my last response, right? So we talked about memory safety bugs. We call a bug a vulnerability. If an attacker, an external person, an adversary, if an attacker is able to influence how the software writes to memory, right? So it goes from being a bug to a vulnerability, right? So my research, as I said, it addresses this class of vulnerabilities. Now, how do we address it? Memory safety issues, they are not new. In fact, since 1990, or even before 1990, it has been a problem. It's common in C and C++, which are C and C. These are programming languages that we use to write low-level software, embedded software, operating systems. They are very common in these kinds of software. And since the ages, researchers have been trying to develop techniques. How do we find these bugs before the software is deployed? Now, the problem is majority of the techniques that they've been developing have been let's call them testing techniques. So basically, in testing we identify a set of inputs and we check, would this software, if I pass this set of inputs to this software, will anything bad happen? Right? The problem with testing is that testing only tells you, yes, your software is safe from just the exact set of input you tried. Right? Now, it's not possible to test with every input. Now, that's where formal verification comes to play. Right? So testing is just, we call it concrete inputs. You test with concrete inputs, or you write tests that, feed concrete inputs to the software. Now, with formal verification, you are not testing with concrete input. You are mathematically asking the question, is there any input for which this software will fail?
Gotcha.
So I'll just repeat. With testing, you bring up a set of inputs and you ask, of these 10 different inputs, will the software fail with any of these 10 inputs, right? But it's easy, but it's not complete,
Right.
right? With formal verification, you don't have a set of inputs.
Okay.
You are just asking the software, is there any inputs within, you describe what we call the input space.
Okay.
So, for example, X can be between 1 and 100.
Yep.
And you're like, is there any input between 1 and 100 or within 0 and the last integer for which this software would fail? And you would need to define what failure means as well in mathematical terms. And then we have these very powerful formal verification techniques. One of them is bounded model checking. And what it does is it does some mathematical things under the hood. I won't bore you with the details, but it does its magic. And then it tells you, yes, if you pass X equals to 1 and Y equals to 5 to this software, the software
Bad things will
fail.
happen, yes.
Right, so that's formal verification.
Yep.
It's a way to mathematically check whether a particular software satisfies certain properties or what under what conditions or what kinds of inputs will make it not satisfy those properties.
Right.
Yeah. So that's formal verification. Now, formal verification, people have also been working on it for decades. The problem with formal verification is, as much as it gives you strong guarantees because it's mathematics, it's hard. It's very hard.
Okay.
It's very, very hard. You need a PhD to do formal verification very well.
Okay.
Right. So it's only companies that can hire PhDs that do it very well.
Yeah.
So what my research has been trying to do is to take a software engineering perspective to this and to ask now the question, and that's where unit proofing comes to play.
Okay.
Is there a way we can make this easier to use for regular software engineers so that a regular software engineer does not know anything about formal verification?
Right.
They don't know anything about mathematics. Like, they may not even know the mathematics behind it. They don't need to know the tools behind it.
Right.
But they still need to be able to check, is there any set of input for which this software will fail? It's something that software engineers need, right?
Yeah.
So we take inspiration from unit test. Unit testing is a very popular software engineering technique, right? Where a software engineer writes tests and tests components or functions in isolation. So they write a function, they can check whether is this function correct. And it's testing, they provide specific inputs.
Okay.
So we take that and we now call it unit proofing, where since we know that software engineers already know how to write unit tests, maybe they can still write unit tests, but now instead of providing concrete inputs, behind the scenes, we tell them, is there any input within the input space? So we use unit proofing as a way to make formal verification, which I said is very, very hard,
Right.
to make it accessible to regular software engineers. So
Gotcha.
unit proofing is the bridge.
Yeah. Okay. That makes sense to me. So you talked a little bit about how you go about finding vulnerabilities. Is it all like mathematics? Are you creating certain scenarios and seeing, okay, this failed when I did this? How does that work? It seems kind of like there's a million possibilities of how it could fail. So how are you finding those?
Okay, so I think that's an interesting question. How I actually finding the vulnerabilities. Okay, I'll continue from where I stopped because everything is kind of sequential. Okay, so like I just said, unit proofing is a way for software engineers to use formal verification. Now, how does this actually work in practice? Because it's through this process that the vulnerabilities come out, right? So how does this actually work in practice? Now, you have a function. The key idea of unit proofing is you don't need to verify the entire software. You just verify one part of it,
Okay.
right? Now, because you are verifying one part of it, it's easier for you to reason about. It's easier for even the formal verification tools. They don't work on huge software.
Right.
They can work on small software, right? So now, given this small software, what we do, we have this technique. It's called assume guarantee reasoning.
Okay.
What does assume guarantee reasoning mean? It means you have a system is usually a combination of components. They are all working hand in glove, they're all interacting with each other. Now, you take one of those components. It can be a function, it can be a set of functions, it can be a module in your software. You take that component. Now, we have a technique called bounded model checking. Now, what you use bounded is a formal verification technique.
Okay.
Now, what you use bounded model checking to then do is, given this particular unit, this particular function, we look for places where the function interacts with memory. Now, for each of those places where it interacts with memory, we add what we call properties. Hey, only interact with this region of memory that is safe. Hey, only interact with this memory if this pointer is safe, right? So we define this. We don't define it. There are tools that define it for us, which makes it easier. Now, we run the formal verification tool. Now, the formal verification tool, we also have a system that it runs the formal verification tool. What it does is to tell you all the inputs for which that particular component is not safe.
Okay.
Now, that is the assume part, assume guarantee.
Yeah.
So we find the set of assumptions for which this particular input, for which this particular unit or function is not safe, meaning bad things will happen if you pass any of these inputs. Now, sometimes not all those inputs are valid, right? So we can tell you, for example, this particular function is not safe if x is between 0 and 10.
Okay.
But if the functions calling this input, this particular function, if they all would pass x equals to 100, that means there's no bug.
Yep.
Because remember, it's only unsafe if x is between 0 and 10.
Right.
If x is never between 0 and 10, it's safe.
You're good.
Right?
Yeah.
So now the second part is the guarantee part. So we take a step back. We look at how is this particular function being used across the system. Mm-hmm. And we analyze each part. We have systems that do that. And we check, are these assumptions ever violated?
Okay.
And if they are violated, yes, we found a bug.
Gotcha.
So it's a two-step process where in the first step, we check what are the set of inputs. We call these assumptions. What are the set of inputs for which this particular, if you pass it to this function, bad things happen. We generate this set of inputs. In the second step, we then check, is any of these inputs like a feasible? Can it occur in practice? Mm-hmm. Right? So we have systems that also do that check.
Okay.
And then once we see, yes, x, in the first part, we see if x is equals to 5, bad things happen. In the second part, we see there is this road through the program from the entry point that the user is calling to this function where x is going to be equal to 5.
Okay.
So once we see that part, a road through the program, then we report it as a vulnerability. Right? And because we've automated each part of this, we can do it at scale. We can analyze multiple functions at a time, and we can find the vulnerabilities easily. It's
a very complex process.
Yes. I think I went into very low detail to explain how the tool works. But as a user, we've automated this so that a user does not need to know any of this.
What's going on in the background?
Right? It's the key idea now is you just take a function in your software, you press play, our magic happens in the background, and then it tells you whether there's vulnerabilities or not.
Gotcha.
So it's now all we are limited at is now the cost of running each of these functions because our system uses maybe API costs, LLMs, which are costly.
Yeah.
So but from a user perspective, it's straightforward. Take a function, press play.
Yep.
The magic happens.
You're a magician then.
Well, that's the fun of engineering.
Yeah, absolutely. Another concept you explore is something called zero trust design for software systems. What does it mean, and how will it change the way developers build software and applications?
Okay. Yeah, so, I'll try to be very non-technical this time around. So we have, everything I've explained so far makes one assumption, that you are the one that is creating the software.
Okay.
Right. So if you are the one creating the software, you can run all these formal verification tools and ensure that everything is correct before the software is shipped out. Now, but in modern software, it's just like when you are building a house. The builder of the house gets every material from outside, right? So your blocks or your steel or your wood, you are getting them from different people.
Yep.
Right. We call those, the supply chain.
Yep.
Now that's the same thing with software. If you are building a software, you don't write all the code. You get software components from different people.
Okay. Yep.
And you stitch them together and they form the software. Now, what's currently happening now is that when you run that software, everybody, all these individual components, they are all running on your computer with the same level of permissions.
Okay, yep.
Okay, let me take a step back. What I just meant was you are taking software from people you don't even know.
Right.
And you are running them on your computer.
Yep.
And those software may have bad things inside them that allows them to steal information from your computer.
Gotcha.
So it's a very risky model, right? I think one way I try to also explain this is you have a house and you have visitors coming into the house, and you have in the house there are all these like nice things in the house. Maybe you have gold or food, and visitors come in and you don't trust any of them.
Yeah.
But now they are free to take anything they want. It's not a safe model.
Right.
Right. So with zero trust, so already before software, there's this concept of zero trust architecture, which is simply when I bring different people into my house that I don't trust, how do I ensure that each person does not have access to do anything I don't want them to do?
Got it. Yeah.
Right? It's easy if it's only two people. Then you can maybe hire someone to just stay and watch the two of them.
Right.
It's very easy. What if there are thousands of persons? You can't watch them.
Right.
Right. And that's the problem with software. In software, you can't watch thousands. You bring thousands of components. You can't watch it.
Yeah.
Right? So we've taken this and we've done some research on what we call zero trust architecture or zero trust dependencies. The key concept is then, if it's not possible to watch all the software at the same time, how can we make sure that each component we bring into our software, we are not the ones that wrote it. How can we make sure that they don't do bad things in our software?
Right.
So they don't steal our information. They don't connect to the network and bring in other bad people. Maybe they connect to the network and download their bad friends.
Right.
We don't want any of those. So we've also built systems to ensure that when you are running third-party, meaning software from other people, you can lock them into their own rooms.
Oh, okay.
So it's more like this software is not allowed to cross this boundary.
Gotcha.
That software is not allowed to touch my food or touch my goods.
Right.
And then we have a way to now determine what each piece of software can or cannot do.
Gotcha.
And then we enforce it. So we now have a security guy that's staying and watching each of them to make sure that they don't do anything bad.
That they're behaving.
That they are behaving correctly.
So if your research succeeds, how does it change the way people build their software? Are you going for like where you build it all in-house, which seems impossible, or how will it change?
Yeah, so that's an interesting question, because I think that speaks directly to the prospective impact of the work we are doing, right? So let's talk about the formal verification part, for example. For example, currently people are using LLMs to write a lot of their code.
Right.
And there is no way to know. So sure, you can test that the code does the good things. So you can write tests to test that the code does what it's supposed to do.
Okay.
But there's no way to know if the code does anything bad that you don't want it to do.
Right.
There is no way, right? And if you look at other engineering disciplines, for example, when people build a bridge, they can tell you, so far the wind is between this and this amount of force. This bridge is safe.
Yeah.
So far the kind of cars driving on this bridge are between this weight and that weight. The bridge is safe.
Okay.
They very mathematically can tell you what's safe and what's not safe. So that's the future we are also and I think even the federal government, like everyone is interested in this future. The federal government has released a lot of circulars. They call them, for example, security guarantees. Mm-hmm. Right? When I take let's say you are the government, you take a software from a third-party company. What guarantees does that third party give you about their software? Right. So we see a future where if we succeed, or we will succeed, right? We see a future where we empower people that create software to also provide a piece of paper that says, we've mathematically proven that this software will not do any of these bad things.
Gotcha.
It may do other bad things. Right. But these bad things, it's not going to do it. Okay. Right? And once we start with the first step, which is the memory safety part, so we say this software is not going to do any of the bad memory safety issues we discussed in the beginning. We can now progress further and start increasing the boundaries of what that software, but it's all about security guarantees. Right. You can say this software, when you build a software, you can say, yes, I've proven mathematically, so it's strong, that this software is not going to do any of these bad things, which is what we want.
Yeah, that makes sense. So what is it like day to day as a PhD student? I assume each day looks different, but tell me a little bit about what you're doing as a PhD student.
Each day looks different, definitely. So I think, for example, what did I do yesterday? I came to school. Usually, I'm no longer taking any class.
Mm-hmm.
So now it's like I'm just working.
Right.
So I come to school, go to my lab. I work in my lab. I eat food when I'm hungry, and then in the evening I go home. Like 9 to 5. Except now it can be 10 to 8 or 7 to
whatever it takes.
Whatever it takes. Yeah. Sometimes it's shorter, sometimes it's longer. So, but then on a day-to-day basis, sometimes I'm implementing. So yesterday, the system I've described earlier that is trying to get all these security guarantees.
Yep.
Sometimes it does not work perfectly well. So I need to. Now this is kind of engineering. I need to run it with cases where it's not working well, study it to understand why it's not working well. And sometimes the fix is just flip a button here and it works better.
Yeah.
Some other times it's like, you need to redesign this entire aspect of it to make it work better.
Yeah.
So sometimes I'm doing that kind of engineering. Some other times when we are writing papers, so for example, once I leave here now, I need to go do some writing. So in that case, now at that point, I have to take a step back from the engineering to now think more, what's actually the core research contribution?
Yeah.
Right. And then I identify what the core research contribution is. And maybe to identify that, some days I have to go and read some papers, right, to see what other people have said about this problem so that I can frame my research contribution as a response to what other people are saying about the problem.
Gotcha.
Right. So it goes from doing the hard engineering stuff to trying to read research papers to understand what the field is saying, to writing papers to communicate the work you are doing and not just communicate what you are doing to the world, but to participate in the research dialogue. So you are communicating and responding to what other people are saying.
Yeah.
So it's always a blend of these things.
You mentioned James Davis, your advisor.
Yeah.
How does he play into what you do? How do you work with your advisor, and what is the importance of finding someone that you can work with?
Yeah, I think that's the most important question for a PhD student.
Yeah.
Like really the most important. I've been very fortunate to have a very principled advisor. And I use the word principled because he doesn't take advising as a let's just do things and see how it works.
Mm-hmm.
He takes it from these are the goals I'm trying to achieve, and these are the strategies I'm going to come up with to achieve those goals. For example, we meet every week. He's very hands-on, but hands-on from the perspective of I tell him, this is the problem I'm currently trying to address, and this is what I'm doing to address those problems. And then he gives me feedback, or he asks questions, those very hard questions that make you to go back to think. And sometimes maybe he gives some suggestions. Okay, maybe you try this or try that. And then if I'm writing papers, then I can write the paper and then I send it to him.
Yep.
And then he reads through it and he tells me, okay, this looks good, but there's always that but. And then he gives some feedback, sometimes in the form of questions.
Yep.
This is not currently addressing this part, or do you want to address that part, right? And then I address his questions or his comments, and then from there we get the paper from just a rough draft to a very sound, polished draft.
Yeah.
He's very hands-on, both in terms of the engineering and in terms of the scholarly aspects of the work.
Great. What's been the most challenging and, on the other side, the most rewarding part of your PhD journey so far?
Oh, okay. I think the most challenging part of my PhD was actually when I started.
Yeah.
Okay, so everything I described about how the system works, it requires knowledge of two things. The first is knowledge of C programming.
Okay.
The second is knowledge of vulnerabilities. Oh, and then there's a third. And the third is knowledge of techniques.
Okay.
Right? Both existing techniques others have used and the techniques I'm currently using. When I started my PhD, I don't know any of this.
Oh, okay.
So and then I started with a project because it was funded by Rolls-Royce, and so I got into the project, and now I needed to learn C, and I needed to learn about embedded systems and learn about vulnerabilities and learn about all while working on a project to address a problem I did not even understand at the time.
Wow. Yeah.
So there was a lot of parts that were playing, and I think it was very challenging at the time. It was very, very challenging.
Steep learning curve there.
I was lucky I had like the support of my advisor and other professors like Prof. Matthew that I work with, who's very knowledgeable in this space and were able to provide me the guidance to succeed. But yeah, I think that's the most challenging part. Then the most rewarding part, I think the most rewarding part is when I see the work I do actually influencing lives outside.
Yeah.
Just 2 days ago, for example, we reported a set of vulnerabilities to one of a popular embedded operating systems. These are like Linux, but they run on small devices.
Okay.
And then because of the vulnerabilities we reported to them, they got to see that a lot of ways their current implementation is very insecure.
Yeah.
And then they re-architected that system. So they have a pull request with more than 1,000 different line changes, which is a huge pull request.
Yeah.
And they did that, like they redesigned a system just because of the work we did and our reports.
Yeah. That's satisfying.
Yeah. There are also cases where, for example, I get access to internships. 2 years ago, in the summer of 2024, I was hired by a major semiconductor company, Qualcomm, to basically study the kind of vulnerabilities that they are having. They had this classification of what vulnerabilities their current systems are able to detect and what vulnerabilities their current systems do not detect. And I was able to study the ones that their systems do not detect, study them in detail, develop new systems or new tools to that can find those vulnerabilities, and then run it on their systems. And then I think I ran it on like 5 of their software and found like 11 vulnerabilities. 7 of them were rated to be of critical severity, meaning these are the worst classes of vulnerabilities that can occur in the system.
Yeah.
Right. And then they had to fix those, and but being part of this directly you are contributing to making a product, and this software are running on like 3 billion devices all around the world.
Wow.
Right. And you're contributing to making those devices more secure, protecting everyday users. I find it very fulfilling.
Yeah. Like you said, seeing the real world impact of what you're doing. What advice would you give to someone who's thinking about doing a PhD?
I think, I thought about this question. I've tried to what's the most important, because there's a lot of advice and you can get it. I think the one that actually still sticks with me is, there are 2 things. The first is the PhD is a marathon, not a sprint. People come into the PhD wanting to change the world on day one or make impact on day one. But I see it more like a long term. In fact, it's not just within the PhD, it's even outside the PhD, right? So I think there are 2 things. There are 2 implications of this, seeing the PhD as a marathon and not a sprint. The first is, in your early days or in your early stages, I think what I tell any first year student is focus on learning, right? And learning is both the engineering part of learning and the scholarly part of learning.
Yeah.
Some days of the PhD may be very hard. Your papers get rejected. The key insight should not be that your paper is getting rejected, but in everything you are doing, you are learning something from that process.
Right.
Either you are learning a better way to build a system, or you are learning more about the research community and what they value, or you are learning more about how do you communicate your work, or you are learning more about the state of the art and what other people are doing.
Right.
But at every stage of the PhD, from the first year, obviously, when you're in your first year, what you are learning is going to be different from what you'll be learning in your 3rd year and in your 5th year, right? But at every point, I think seeing the PhD as an opportunity to learn.
Yeah.
Right. And then you learn. I think the second thing, and this is a very quick one, is also I have this focus. I don't just want to do research to contribute to scholarly knowledge. I want to do research to help the world, to solve real problems.
Yeah.
Right. And I think it's something that has guided me towards the kind of problems I've picked, towards the kind of work I've done, towards the kind of papers I've written or chosen not to write. Yeah. It's always who is this going to help, and what problem is this going to solve? And will I be proud of this? And I think it's an ideology I always recommend to especially people who are starting their PhD and looking for what problems to start solving. Think about impact. What impact is this going to make, either in the scholarly community or in the engineering community? Yeah,
because if you're not passionate about what you're doing, it's going to be hard to get through a PhD program.
Exactly, because it's very hard. There are days that are challenging, right? But yeah.
So when you're not doing all your vulnerability checking, what do you like to do in your free time?
Oh, well, what if I say vulnerability check it?
It wouldn't surprise me. It wouldn't surprise me.
But I mean, I like talking.
Yeah.
So I also like talking with my friends. I like hanging out with them. Most of my friends are not here, so I get on phone calls with them and I talk with them. I also have this. I've always admired people that play the keyboard or musical instrument. So I recently got a keyboard and I started learning. So sometimes in my free time, I have this book about piano, and then I have some lessons on my iPad, and then I use it to.
Oh, that's cool.
It's very relaxing.
Yeah, and exercising a different part of your brain too. So that's really great. Yeah. Well, Paschal, thank you so much for sharing your journey and for giving us a glimpse into what it's like to be a PhD student here at Purdue.
Yeah, thank you very much for the opportunity, and have a great day.
Thank you. From unit proofing and formal verification to zero trust design, Paschal's research is helping move us toward a future where engineers can catch vulnerabilities before they ever reach the public. So thanks so much for tuning in to Engineering Innovations, the official podcast of Purdue University's Elmore Family School of Electrical and Computer Engineering. If you enjoyed this episode, be sure to subscribe and share it with a colleague or a student who cares about the future of secure and reliable software. Also, leave us a review or comment on what people or topics you'd like to see next on the podcast. Until next time, I'm Kristin Malavenda.